Hello, math humans. We're going to do 3.3 today. We're going to be talking about conditional probabilities. So our objectives are conditional probabilities. So now that we've seen this word for 3 times, a conditional probability is a probability that an event will occur if, and this is the critical statement for a conditional probability, some other condition has occurred. And so we would write it the probability of A given B. And so here's the words for what this represents. So we're just going to jump right in with a couple of examples. So the first one, 2 cards are going to be drawn from a shuffled deck. This is important because this creates random. It means that the cards haven't been prearranged. This is a key component for this particular problem. So without replacement means that I'm going to draw a card and keep a card. That also means that on the second draw, there are less cards because you kept the card from your first draw. So we want to find the probability on A that the second card is a heart, given that the first card is a spade, right? And so if we were to write this, it would be probability that second card is a heart, given first card is a spade. Okay, so just a little bit review. Remember that there are 52 cards in a deck. On the second draw, we're going to have 51 cards. Remember that there are 13 cards in each suit. Okay, which means that there are going to be 13 hearts. So this is actually just a pretty simple probability still. So we would write that the probability of the second card is a heart, given that the first card is a spade, is going to be there are 13 cards in a suit, and then if I kept the first card, that means when I draw the second card, then I have less numbers to choose from. Alrighty, now let's do the second example. So this one says the probability that the first card is a faced card and the second card is an ace. Okay, so let's work on this example. So the probability that I get a face card, and remember that face cards are king, queen, jack, and there are 4 suits, so there are 12 of those. So that's going to be 12 out of 52, okay? Then the probability that the second card is an ace, there are 4 aces, and remember now the denominator is going to be 51 because we did not replace that second card. So then if we finish this example, I'll do it over here. So then the probability that the first card is a face card and the second card is an ace is going to be the probability of the first card multiplied by the probability of the second card, which is 48 out of 2652, and that's going to be reduced to be 4 out of 221. And remember, you can do this in your calculator, and once you've entered this into your calculator, you're going to math frac it, which is lovely. Let me just re-show you that in case you don't remember. So if I have 48 divided by 2652, I get a decimal, and then I math frac it, and I get the 4 out of 221. So we love our calculators. Okay. The next example, still kind of in the same genre, is that the probability that the one card is a heart and the other card is a club. Okay? So as we move through this example, remember that there are 13 cards in each suit. In this particular problem, there's actually 2 different ways that this can happen. So notice that it says, it doesn't say the first card, it says one card, or a card is a heart and the other is a club. So this could be the probability that the first card is a heart and then we get a club, or, this is going to be our key word, we get a club first and then a heart. So those would be the two different ways that that could potentially happen. These are independent events. So remember that the probability of or, and I'm going to call this probability A and probability B. So the probability of A or B is the probability of A added to the probability of B. Okay, so then let's do our individual probabilities. The probability of getting a heart is 13 out of 52. Then the probability of getting a club is going to be 13 out of 51, because remember, we're still doing without replacement, so that means that I have one less card. So then if I talk about my probabilities, okay, and I didn't leave myself quite enough room, this is going to be, I'm going to write it right here, the probability of first getting a heart, then a club, or the probability of getting, oops, sorry, I don't need to write that again, a club and then a heart. Okay, so if I manage this one, this is going to be the probability of a heart is 13 out of 52 multiplied by the probability of getting a club, 13 out of 51, plus, because this is my or, and then I'm going to have the probability of getting a club, 13 out of 52, and then a heart, 13 out of 51. And so if I multiply all of these fractions together, I'm going to get 0.127, so that is 12.7%. Okay, so notice what I did. The probability on the first card of getting a suit is this, and then this is the probability of the second. The or means I'm going to add the two probabilities together, and then I did the same probability. This is the club, this is the heart. Alrighty, so the next thing that we're going to do is we're going to move to example 2. And example 2 says 2 fair dice are rolled and the sum of the numbers is observed. So we're going to do a dice chart, and I already have that done for us. We want to find that the probability that the sum is at least 9 if it's known that one of the die is a 5. So this statement right here, if it's known, is going to give our conditional probability. So I'm going to go ahead and move to a dice chart. Ta-da! So there's my dice chart. And so then I'm going to use this information as I process. So notice this is all of the possibilities for the first die. These are the possibilities for the second die. And then I have all of my sums on the inside. I've also written that the numbers where a 5 is included. So notice this would be a 1 on the first dice and a 5 on the second. And so I have all of these numbers that include a 5 on one of the two die, and all of these numbers that include a 5 on one of the two die. So notice that having doubles, having 2 5s, is rolled technically, and we count it in both things, but we want to make sure that we don't count it twice. So we're going to only count this one. Okay? So the probability of getting the sum is at least 9, given that one die is a 5. Okay? So I'm going to call this event A and this event B. Okay? Alrighty, and so if we look at our dice chart, so there are, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 ways to include a 5. Okay, and then if we look at the sum, so it says the sum is at least 9. Okay, so there are, this one is 8, this is 9, this is 10. So there are 5 where the sum is at least 9. Okay, so if this is my sum is at least 9, so I'm going to have 1, 2, 3, 4, 5, 6, and then I have 5 of those numbers have a sum of at least 9, okay? So the sum is at least 9, means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 5 of those, 1, 2, 3, 4, 5, are going to be included, okay? So I'm going to just circle those so we can see those. So there's 1, 2, 3, 4, 5. At least 5 of the die that have a 5 in it have a sum that's at least 9, okay? So then, because we're looking at where the two things overlap, the probability of, can't see that, sorry, my bad, the sum is at least 9, given that one die is a 5, is going to be, here's our 1, 2, 3, 4, 5. There are 5 out of 11, okay? All right. The next thing that we're going to talk about, and I'm just going to do this before I show you our example, is the multiplication rule for probabilities. Alrighty, so let's say I have the probability of A and B. This is going to equal the probability of A multiplied by the probability of B. And we've actually done this in a couple of our examples. Okay, so then that just gives us an official definition. And then I'm going to add a conditional probability. So if I want the probability of B given A, notice that the order has changed. Instead of A coming first, now B comes first. This is going to be the probability of A and B, which is this right here, divided by the probability of A. Alrighty, so now let's go to example number 3, and I've got it written out for us ahead of time, and it's a little bit hard to see, so let me see if I could zoom in a little bit to make that better. Oh, look at that. So example number 3 says 250 people recently purchased a car and were questioned, and the results are summarized. So notice what we have. So I have 250 people, here's the total, that bought either a new car or a used car, and they were either satisfied or not satisfied, okay? So the total of people that were satisfied is 175. The total of people that were not satisfied is 75. The total of people that bought new cars is 120. And the total of people that bought used cars is 130. So we're looking for what's the probability that a person is satisfied if it is known that the person bought a used car. So this statement, if it as known, is going to create our conditional probability. So here's the information that we were given, and then I want the probability that a person is satisfied given that they bought a used car. So this is a conditional probability, A-B-I-L. Oh, that's a long word. So I want the probability, and I'm going to write that this is B and this is A. So I want the probability of B given A. Actually, I lied. This is B given A. Make that a capital A. So it's the probability of A and B divided by the probability of A. So if we make that have words that fit, this is going to be the probability that I have satisfied and used divided by the probability of used. Okay? And we're going to pull that information from our chart. So the first thing I'm going to do is I'm going to write my probability of used. And if I look at the chart, there were 130 people that bought used cars. So that's 130 divided by 250. And I can reduce the zeros and make this 13 out of 25, or I can use the 250. Either is okay. So then if I look at the probability of A and B, which is the probability of satisfied and used, so satisfied and used, right, would be right here where those two pieces intersect, and I guess you can't see that, but here's my used, here's my satisfied. It's going to be 83 out of 250. So because I can't reduce this one, I'm going to use this 130 divided by 250. So then my probability of B given A is going to be the probability of and, 83 out of 250, divided by the probability of used, which is 130 out of 250. Now, if you'll remember, if you have a fraction divided by a fraction, that means that you need to flip the bottom fraction. So here's my 250. There's the numerator. I'm going to flip this guy and make it 250 over 130. These two numbers cancel, so I get 83 out of 130. So then my probability of B given A is going to be 83 out of 130, which is 0.638, which is 63.8%. Alrighty, so I have one more example for us, example number 4, okay? Alright, so in this one, I have a survey of 350 students at a university revealed that the following data is true. So it's about class standing and place of residence, meaning where are they living while they're in college. So if you'll notice, let's look at our table. I have 350 total people. I have people that are living in dorms, apartments, and with their parents. This was me in college. I lived at home for the first 3 years. And then I have freshman, sophomore, junior, senior. Okay, and then these are my totals of those columns. So I'm wondering, what is the probability that a student is a sophomore if that student lives in an apartment? So if that means that we become a conditional probability. So remember that the problem tells us that I have 350 students that were surveyed. So the probability that a student is a sophomore if the student lives in an apartment. So this is a conditional probability, and it's the probability of B given A. So it's the probability of A and B divided by the probability of A. So let's manage our individual probabilities. The probability of A, which is the probability that the student lives in an apartment, okay? So if we look at it, here's our apartment, and notice that we had 119 students living in an apartment. So this is the 119 divided by 350. So then we want to do the probability, see if I can see both on there, of A and B, which is the probability of being a sophomore and living in an apartment. So if we look at our list, sophomores that live in an apartment are the 17 out of 350, okay? So now I'm going to do my calculation. The probability of B given A is the probability of A and B divided by the probability of A. So the probability of A and B was the 17 out of 350, and we're going to divide it by 119 divided by 350. Remember that a fraction divided by a fraction, I flip the bottom fraction, so this is 350 times 350 over 119. The 350s can cancel, and so I get that my probability of B given A is going to be 17 out of 119, which is 0.143, which is 14.3%. Alrighty, so then that would be the probability of our sophomores that live in an apartment. Alright, my dears, that is it for today. I will see you